So I'm Harry Lewis. Nice to see you all. Sorry I wasn't there last night. And I'm not going to do much of a way of an introduction here because we've got an incredible panel and an incredible main keynote speaker for this event. But I do want to welcome you to Maxwell Dworkin. This is the home of computer science at Harvard, and to the School of Engineering and Applied Sciences. And let me urge you to look around this building, because at our 50th reunion, I'm going to host you at the new campus that will have been built by that time in Allston on Western Avenue, which is where we will all, in principle, be by that time. And I suggest that we hold the 50th reunion until that campus is finished, which will delay the aging process by a few years, because I think the campus is actually not going to be open in 5 years as is planned, but that's what we're telling us that we're being told to plan on. I'm only going to introduce my colleague and friend, Jim McCarthy. You have bios on all of the panelists. It really is a wonderful group, and I want to thank you all for doing it, for taking the time to do this. And I'm going to hand, after I introduce Jim, I'm going to sit down, and after Jim stops speaking, Al Boatwright will moderate the panel and will moderate, I'm sure he will be immoderate in his moderation actually, but he will control the flow of events. And we've tried to structure it so there'll be plenty of time for conversation with Jim and with our distinguished panelists. So, you know, it's a rare privilege to introduce such a close personal friend and deeply respected colleague as Jim McCarthy. Jim and I have worked together on a variety of things at Harvard for years, because in addition to his amazing scientific career, he is a professor in 2 departments, not only organismic and evolutionary biology, but also earth and planetary science. And you know, for those of you in academia, you know that is an unusual activity, because you have to convince 2 sets of faculty to take you on as one of their peers. And it's a great sign of respect. And he is the Alexander Agassiz Professor of Biology. Some people occupy chairs that are named after really good people. You can go look up who Gordon McKay was if you want to know who the donor of my chair was. And I'm not going to go through all of his scientific career and his amazing contributions to earth and planetary science, and to, most recently, the important work he's done, scientific work he's done related to climate change. But I do want to say that one of the distinguishing features of Jim is that he is a true citizen scientist, a scientist who lives and breathes not only his science, but its significance for all the rest of us who live in this world. And he is, in fact, right now serving as the chair of the board of directors of the Union of Concerned Scientists. So he's an extraordinarily busy man with all that. And I got to know him extremely well, in part because on top of all of that, he was master of Pforzheimer House, what some of you may remember as North House. And that in itself can be a full-time job. And he and his wife, Sue, were wonderful, wonderful colleagues while I was dean and he was serving as master. So, Jim, thank you for enlightening us.
Thank you, Harry. It's a real pleasure to be here. Is the audio okay? Yeah. Everyone here in the back? So you see a title up here, Disruptive Weather, the Oceans, and Climate Change. I'm going to give a little bit of an overview on what we know about climate these days. A month or so ago, we had the release of the latest installment of the report from the Intergovernmental Panel on Climate Change. I'm going to talk a bit about disruptive weather and how the ocean has an important role in that. So I'm not going to spend much time on several of these slides. I'm happy to come back to them, but I think a lot of this is just generally known. But if the Earth is warming as a result of additional greenhouse gases in the atmosphere, you would expect all of these processes to be changing in the direction of the arrow. And the data confirm this. There's no exception to what you would be expecting. And we could also talk about the upper atmosphere, where there are some changes that, again, they might intuitively not seem like you would expect them, but if you look at what we know about how the atmosphere works, they're consistent as well. It's been colder in the past. I love this picture, 1911 Niagara Falls. The little dots here are people. They're out here in their top hats and finest attire, walking over the top of the falls and around the base here. We don't see that anymore. This is the compilation of the 3 records that we look at to see globally whether there is a consistent pattern in the change in Earth's temperature. One of them put together by NASA, one by NOAA, and one by the British Met Office, the Hadley Center. And these are compiled by the World Meteorological Organization. And the different colors in here signify the different sources. This gray shows an air bar. And this is that period in the early 1900s when it was cooler, warmed, then a period in the mid-century. It either didn't change much or actually cooled, and then takes off in the 1980s and has been warming since. So one of the important pieces of understanding this, of course, is not simply that the climate is changing, but it's changing in consistent ways that can be explained by the underlying science. And although we know over this period greenhouse gas has been rising steadily, we also really understand today what happened here, and actually what happened here. And if you want to bin the data, this is the kind of picture you get. You know, every year of the 2000s is warmer than the average for the 90s. Every year of the 90s warmer than average of the 80s, and so on. Here's that period in between, and then further back where temperature was cooler than the average over this period. So there are no data that are inconsistent with this trend. And even people who have set out to try and disprove the validity of all these surface temperature measurements or the ocean temperature measurements as somehow being biased because of where samples were taken or how they were processed have been unable to do that. Now, in terms of what this means for weather, we find that there are some consistent patterns that emerge there as well. This shows, ignore the graphics for a moment, but this trend from 1950 to 2010, which are cold nights, the frequency of unusually cold nights, declining rather consistently since the 80s. Cold days, declining rather consistently. If you look at the data for warm nights, rising, warm days rising. So this is a pattern, and these are again global averages. You could tease this apart and see how these patterns vary day and night, cold and warm. But basically, if climate were stable, you'd expect records to be broken for cold nights and cold days, the same frequency as warm nights and warm days. And that began to shift in about this period in the 1970s, and from then on, we see a heavy tilt. Many more warm records, night and day, far fewer cold records, night and day. Now, I'm going to skip over these. I've got some statements here, but if anyone's interested, all the professional societies, every single one that includes scientists who look at climate have made statements on this. All the academies of science that have made statements on this, which are dozens worldwide, have said something similar to what we have here. Observations throughout the world, clear climate change is occurring. Rigorous scientific research demonstrates greenhouse gases emitted by human activities, the primary driver. Now and then, I won't go into these, but these are again specific statements. Now and then people say, well, is there something even more solid than that? And it suggested this graphic may be one of the best pieces of evidence that no one will argue with that. Now, if we turn to the ocean a bit, this is a very, very powerful story and an important part of the understanding that's occurred over the last couple of decades. Just concentrate for a moment on this red line, which snakes up, snakes down, up, flat, up, and then rises steadily. This is the content of heat in the ocean that sits between the surface and 2,000 meters. Now, when I was in graduate school, a long time ago, I'm a couple years younger than you, just a couple. If one had said to any of us working in the North Pacific at that time that in my lifetime, there would be a point at which the temperature at 2,000 meters would be warmer in the North Pacific than it was in the 1960s, and every decade before that for which we had data, we would have thought it inconceivable. The surface, yeah, 100 meters, yeah, but 2,000 meters, you would have said, I don't think it's possible. And yet, throughout the world's oceans today, you see at 2,000 meters, the Earth is warmer than it was just a few decades ago. Now, this black line is the deeper ocean below what we call the main thermocline and 2,000 meters, which is the average depth of the world's ocean is about twice that. So this is mid-depth. And notice this steadily increasing in this manner, but here's the really important point. These whiskers are the air bars. And notice what happens to these whiskers at about this period, and notice how small they get. Here, it's a shaded gray, and notice how it telescopes in. So what we have is a new data set that emerged in the 2000s as a result of a really extraordinary global effort. It's called the Argo Drifting Float. This is a float that starts at the surface, descends to 1,000 meters, and drifts for 9 days, wherever the ocean takes it for 9 days. On the 10th day, it drops to 2,000 meters. The scale isn't really shown here. It would go deeper, and goes back to the surface and says, hello. Satellite picks up the signal. You know where it's been. You know where it was 10 days ago. You know where it is now. So that tells you what the ocean is doing at 1,000 meters. All along that path, it tells you what the temperature was, what the salinity was, and at the location which it pops up, it tells you the salinity and temperature down to 2,000 meters. So this has given us increased precision, as demonstrated in that last slide, on the understanding of ocean heat content. There are over 3,000 of these moving around the ocean. The colors here indicate the nations that participate. There are over 24 nations that participate in this effort. And so this is what has given us this new confidence in understanding how the ocean's heat content is in play. Now these units, I think these are zeta joules on the left here. The joule, and best explain it to undergraduates as saying it's the energy you find in about 5 teaspoons of beer. This is a lot of beer, but they can understand that. And if you go forward from 1970 to 2010, these different wedges show you how much of the heat that has been trapped by this additional insulation in the atmosphere is apportioned in these different components. Now at the very bottom, this little purple wedge here, that's how much of it is still in the atmosphere. This, the brown wedge, that's how much of it has warmed the land surface. The white, how much has gone to melting ice. This dark black, this is the deep ocean, and here's the upper ocean. And so if you look today at how much of the energy that is being held by the system as a result of more insulation in the atmosphere, 90% of it is in the ocean. And here, if you go back and look in the 1980s and say, you know, you couldn't even say with these air bars, this is 1980 going forward, whether it was plus or minus. And yet notice how the air bars telescope in and now give us this small uncertainty about this total number. So my point here is that this understanding of the ocean has been a very important part of balancing the heat budget that is such an important part of understanding not only how climate works today, but projecting how it will work in the future. Now, I'm going to jump to the Arctic. This is the early 1990s. This is a Russian icebreaker. This wonderful mouth painted on the front of it. It's a nuclear icebreaker. You can barely see a little window up here. They're square windows on the bridge, about the size of my pointer dot. They're a meter high. Look at the crack here from this icebreaker crashing through the ice, and look at the thickness of the ice. It's like 3 or 4 meters thick. And this is in the central Arctic, within a few tens of miles of the North Pole, early 1990s. This is, I'm in a small helicopter. I took this picture up close. You see this, it'll go through ice of that thickness. It's a heck of a ride, very noisy, but it will eat right through it. 75,000 horsepower. This is 2004, within 50 miles of the North Pole. Same ship, they painted the mouth off it, but look at the thickness of the ice. Now, while that could seem anecdotal, it certainly is, here's what was happening. So here in the 80s to 2000, an average for the thickness of ice, which is correlated with age. So here's the thickest ice, 6 years. Here's the thinnest ice, which would be less than a meter. Here's Greenland. Here's the Canadian archipelago, the north coast of Russia. Look at the old ice here in the central Arctic. Those particular shots were taken as we went from Franz Josef Land to the North Pole, which is about here. And here now, look at 2008, Franz Josef Land to the North Pole. You would get out of thin ice into 1 year ice, 1 meter ice, into a bit of thicker ice, but not very much. So we've basically lost the old ice from the central Arctic. This was July 29th, 2000. This picture appeared on the front page of the New York Times, and the response to it from many was, I don't believe it. Couldn't happen, couldn't be. I could show you a pile of mail like this. Some email at that time, but a lot of letters, people in absolute disbelief. Today, no one would doubt this. So if we look at the annual ice record in the Arctic for sea ice, winter, these are months of the year here, January through December. Ice is at its maximum extent. This is area again. In the summer, it reaches its minimum about September 15th. Here was 2012, 2012, which is the lowest year on record. 2013 comes in at a tie for the 6th lowest. And layered in here are the last 6 years, or tie for 6, last 7 years. So all of the recent years, the last 6 years, the last 7 years have been the lowest years on record. If you go back here, you'd find 79, 80, 81, 82. This is a 30-year record from satellites first measuring sea ice extent beginning in 1979. It wouldn't surprise you that with sea ice this year not breaking new record, there were people writing, well, must be recovering, don't have to worry. In fact, look, sea ice is forming at a very rapid rate now, which it does every year, but in fact, there's no question about the consistency of this trend, and you can see it dramatically here, what's sometimes called the sea ice death spiral. These are months of the year in 1979, all packed here, that are normalized to that year, so they're all 100%. And as you move each of these slices of the pie is a year, so we've got sort of 33, 34 years here now. So 2013 is out here. We have only a few entries for 2013. Most of these are still 2012. But the summer sea ice is now at about 25% in volume, what it was in 1979. In the winter, it's about 60. So there's no question about not only what's happening, but the consistency of this trend. Certainly there are some years in which it will dodge one way or another, but it's definitely spiraling inward. Now, one of the challenging things for people concerned about the Arctic has been nobody seems to care about the Arctic. Remember, this sea ice, were it to all melt, doesn't affect sea level because it's already displacing the water of its volume as it's floating. And so unless you're really concerned about polar bears, should you worry about what's happening in the Arctic? But what we know now is that the ice in the Arctic, by insulating the ocean, keeps heat within the ocean that without the ice escapes to the atmosphere. And as that heat escapes the atmosphere, it creates convective cells. The atmosphere warms all the way to the stratosphere. And this vortex, called the polar vortex, the polar jet, this is what gives us a path of the jet stream, which you see on weather news, which I'll say a little more about in a moment. And as more heat is lost from the central Arctic, the strength of this jet diminishes. And you see that more cold weather escaping out of the north into regions further south. And in fact, more warm weather, as we'll see later, as this undulates, moving north. So as we've set some cold records across the northern parts of the United States in a few areas in the last couple of winters, and in Russia as well. 2010 in Russia was a bitterly cold winter. We've also set warm records further north. We set warm records all across central and northern Canada and further north in Eurasia. So we now know that there are linkages between sea ice in the Arctic and weather patterns which are occurring right where we live. This kind of paper, we're seeing many of these in the last couple of years, large-scale atmospheric circulation changes associated with recent loss of Arctic sea ice, as people are piecing this together in a highly quantitative way. Now I'm going to jump to sea level, which is, of course, another way that changes not with sea ice, but ice at high latitude will affect all of us living anywhere near a coastline, no matter where we are globally. Sea level, of course, as you know, can change with ice melting in land, flowing into water, with land rising or sinking as a result of either pumping groundwater or being unweighted as ice retreats. We know that sea level rise measured with a fair bit of uncertainty through the 1800s and 1900s, because these are tide gauge data showing this upward pattern, maybe 1 millimeter per year, then 2 millimeters per year, but very precise data beginning in 1993 with radar altimeters, which are measuring the height of the sea surface. And we now know that this rate is order 3 millimeters a year. So one could see that this pattern is one of not only increasing rate, but we could say acceleration. So in 2000, really 1998, 1999, and 2000, I was heading one of the working groups, the Intergovernmental Panel on Climate Change, and as we were reviewing all of the science about Greenland, we felt comfortable saying that there wasn't any pattern of change obvious at that moment with respect to ice on Greenland that caused us concern about the stability of Greenland ice over the current century. Next few decades, for certain, not anything that looked at all troubling. And within 2 or 3 years, it was clear that we had been wrong. This is a sort of pattern to begin to emerge just a couple years later. So there'd always been in summer this bit of the ice on Greenland, the surface temperature of which during the summer would be above the melting point of water. This white line is a 2,000 meter contour. So Greenland rises steeply at the edges. It's got a broad, flat dome, rises to about 3,200 meters at this point. A few years after we finished this work, this is a sort of pattern that was beginning to appear. This was growing dramatically, this area of summer melt. And here is one of the first satellite images published in journal Nature in 2004, in which you could see, this is bare ground, and this is the image for 2001, 2002, and 2003, and this indicates a melt line where this line is. So the slope is showing a higher and higher melt line, and you can see some little dots emerging here. Here's a blow up of that last one. These are melt pools. And I had the opportunity in 2003 to fly up over the ice cap and actually photograph these. And it was, for many people, the first time these images had been seen. I gave them to this guy, from class of '85, and he put them into a film and won an Academy Award. He did give me a credit. Look at last summer, 2012. There was a 4-day period in which the entire surface of Greenland was above the melting point of water. Now, ever seen before? You can't say no, absolutely, never seen before. There's some evidence in ice core records. There's a period in the late 1800s where several areas in Greenland seem, but it's not, you can't map all of the surface of Greenland in the, retroactively for the 1800s, but this is alarming. It's clearly a trend that nobody anticipated a decade earlier. So if we look at sea level rise from 1970 going forward, this data to 2010, this lower line is a component of sea level rise which is due to what we call the thermospheric effects, the same phenomenon that causes mercury to swell. It's in a confined capillary in the thermometer, so it has to rise. It can't go out, can't go down, it rises. The same with the ocean. The ocean warms, it rises like mercury in the thermometer. This component, this wedge that you see growing at a more rapid rate, is that or difference, I'm sorry, between this and this wedge is that due to ice melt. Now, small glaciers, you know, wasting like crazy, Glacier National Park and all over Alaska and in the Andes are a very, very small component of this. Most of what's happening now is loss of ice from Greenland. And from that, we begin to see in the late 2000s papers that were making much greater projections for sea level rise. This is one that was published in the journal Nature, saying that it could be as high as 2 meters by the end of the century, although central tendencies seem to focus around 1 meter. Now let's look for a moment at something we will see an anniversary of next week. Superstorm Sandy, 29 October, 159 dead, 650,000 homes lost, $50 billion worth of damage. A Category 1 hurricane moving up the coast behaved very strangely. First, it remained its strength. It didn't dissipate, but you know, Irene did that the year before and came up through here. But this sharp, sharp bend west, what on earth was that? This is a forecast. This is a forecast. You see days out. They were forecasting it would bend in. The Gulf Stream during this period, temperature being indicated here, exceptionally warm being in red, cool being blue, was at all-time record temperatures. So a tropical storm is fueled by warm water. They do not spin up in cool water. They dissipate if they spin up in warm water and move over cool water. If they come through the Gulf of Mexico and hit a patch of warm water like Katrina, it can go from Category 1, 2, 3, 4, 5 with that patch of warm water. So this tropical storm escaped the tropics but remained fueled by the exceptionally warm waters of the Gulf Stream. Now come back to that comment I made earlier about what's happening with the jet stream. What we're seeing are these larger undulations now as a result of the changing dynamics of the atmosphere over the Arctic. And here is Superstorm Sandy coming up the coast. We have here a blocking high. And so the high pressure cell has winds moving this direction. This is a low pressure cell, so the winds are moving this direction. So right at this point, between the low and the high, we have strong forces which are going to pull the storm as it did right on shore. So here's a very unusual situation in which you have exceptional damage as a result of an intense storm. Was it caused by climate change? No, you can't say that. But had it not been for higher sea level having risen over the last century, had it not been for an exceptionally warm Gulf Stream to keep this fueled, had it not been for this exceptional blocking high that caused it to steer inshore, there's only one thing that would have made this a really exceptional opportunity for a storm. It was a full moon. So 3 of these things are linked to anthropogenic climate change. 1, the full moon, which would be higher tides, the full moon, was a natural phenomenon. Now, as you think about this blocking high, a meteorologist would say, well, yeah, it's a blocking high. Those are always pesky. So how many other really exceptional climate weather-related disasters in the last decade have been due to exceptional blocking highs? Heat wave in Europe in 2003. 70,000 people died in that heat wave, summer 2003. What was the explanation? Oh, blocking high. Never seen one like that. Russia, not only winter of 2010, but then summer of 2010. 50,000 people died in Russia in a heat wave, summer 2010. What caused that? Blocking high. Most extreme ever. So the pattern in these blocking highs is part of what I said. People are now beginning to sort out and unravel the actual mechanism whereby the change in the dynamics in the Arctic or change in the jet stream are giving rise to these intense weather systems. Now, just jumping forward and drawing this to a close, I'm going to talk about some of the projections from the IPCC most recent report. I'll skip this one, come back if anyone's interested later. But basically, they're using 4 scenarios, and these are plausible futures. There is one that includes substantial efforts to control our releases of greenhouse gases, and one that says, go for broke, business as usual. This this shows, by the way, which one we're on. We're on the go for broke one. And what you have here is global average surface temperature change that would occur if we continue on this trajectory or worked hard to move to this one. Now, the reference point here is 1986 to 2005. So if you want to think, as we often do, about increase over the last century or so, that is, you would see this rising to something a little less than 2 Celsius, but it would be over 2 if you add the heat that has been held by the atmosphere over this period of time. And this one, likewise, rather than being about 4, would be more like 4.5 or 4 3/4. The numbers here indicate the number of general circulation models. We call them Earth system models now, which have been used. And if you look at how that's distributed, you see, of course, here's the low scenario, and color being cool, warm, and then exceptionally warm. This is the high scenario. And look at the high latitude in the Arctic. You see this up in the 9 or 10 C. And again, if you're not comfortable with C, just double it is close enough. So think 20 degrees Fahrenheit warmer in the Arctic. And so what does it say about sea level? Again, these two scenarios, one would come in with a value here, which looks like something, this is 1 meter here, about 4/10 of a meter. This would come in at something looking like something on the order of 8/10 of a meter, or about 30 inches. And that's the mean. So the extreme, or the full range would go up to a meter. These, again, the recent, and I would say conservative IPCC assessments. But here's the untold story about sea level rise. It's not uniform. This uses an older projection of 38 centimeters. This is a paper published in 2011. And this line confines the area in which, the solid line, which would be greater than or less than the average. And look, folks, where we live. This is, rather than the average of 38, we see that we're up into 2 or more times that in this area off the East Coast. This has to do with currents. It has to do with where the ice is melting. That is this area off Greenland, the major contribution to this. And if we look at what the implications would be East Coast to West Coast, you can see, in fact, depending where you are, this would have very different implications if you're planning on an average sea level rise. We take that high scenario from IPCC and they give this projection. You lose a color out here, it just tapers off to a little point, but that's where we are in this area off the northeast coast. So I want to finish with just two final slides. This shows how serious the problem is or how serious it isn't. So from 60s, 70s, 80s, 90s, 2000s, growth in population, growth in emissions, per capita GDP, and intensity of GDP. This is good news. It means we're getting more and more efficient with the use of fossil fuels. Now, some nations do that in an artificial way. You export, send offshore your manufacturing, become a service industry. This makes this number work good for you, but you've got to be sure it isn't being offset somewhere else. But if you sum all these up, here's the scope of the problem. It's a 2% problem. If we could reduce emissions 2% a year, you address this problem. And think about it. How hard is that? How hard is it? 2% a year. So Harvard University, with Drew Faust's plan from 2006 to 2016, is a 30% reduction. The city of Boston, Mayor Menino's plan, which I'm a great champion of. I was on his task force. I saw this work. The mayor said, give me a plan. I want to see what it looks like to reduce CO2 emissions in my city of Boston. Everything that happens here, not just by the city, but everybody who comes to the city. Everything happens in the city. 20% between 2010 and 2020. And we came back with a plan, and he said, oh, it doesn't look that tough. What's 25 look like? So we came back with another 25. He said, we're going to do it. And we're going to hear more about this, I hope. But look, there's no one thing here. There are all of these little pieces. And it's on track, doing it. So around the country, cities. Boston was recently ranked #1 in the nation among the 34 most populous cities. in its success in reducing greenhouse gas emissions with energy efficiency. So this is not a big problem. And cities around the globe, not just in the US, not just the cities we hear about all the time, Seattle and San Francisco and Boston and New York, but around the globe are doing this. So in places where the governance is such that the person running the operation really has to be accountable to the constituents, you get rid of some of the partisan nonsense, you're proving that this is actually doable. So I will end there. I think 1 minute over.
Silk will be our next speaker.
Thanks.
As soon as we get her hooked up.
So I'm another academic, and of course, that means another PowerPoint. So you've heard from an oceanographer. I'll give you the botanist's perspective on global change, giving you just a few examples of impacts on life. I'll talk a little bit about how species are moving around in response to global warming, how food production is being affected, and both of these problems are intimately related to the nitrogen cycle. We've been talking about carbon dioxide and carbon cycling, but as a biologist, I'll be drawing your attention to the role of nitrogen. So we heard a lot about the melting of sea ice, and of course, we can imagine immediately that this is a loss of habitat for the polar bear. But actually, the impact is much greater than that. We have these nutrient-rich air pockets in the sea ice, which is where the tiny microscopic algae can thrive. And with the melting of the sea ice, the algae sediment and are lost to the food chain. The little animals which like to eat the algae also disappear. The fish which eat the little animals have a hard time. The seals which like to eat fish start to be in trouble, and the polar bear which eats the seal is impacted too. So in addition to losing this physical habitat, the whole food web is disruptive. We're seeing these massive habitat shifts in North America. The most vulnerable species are those that are found the furthest north and at the highest altitude. So for instance, our north temperate forests are displacing the smaller stature plants that populate the previously frozen areas. And this impacts all the Arctic animals such as caribou and the snowy owl. Everywhere in the United States, people are reporting that the birds and the butterflies are migrating earlier than they used to. They may run into food availability problems as a result of this. And farmers are recognizing that they may need to change their crops. A couple of dramatic examples. Apparently in a region of China where farmers have been growing potatoes for generations, they're now being told to learn to cultivate bananas. A French colleague tells me that the champagne industry in France has bought up land around the White Cliffs of Dover, which is thought to be the best climate for growing champagne grapes in another generation or two. So as a biologist, when I think about what living things need, I think immediately about nitrogen. It's part of those basic building blocks of both plants and animals, our proteins and our DNA. And so we need to have lots of these building blocks to grow and reproduce. But paradoxically, nitrogen is one of the most abundant elements in the biosphere. Our atmosphere is 80% nitrogen gas. and yet this nitrogen is not available to plants. Neither plants nor animals have the ability to combine nitrogen with hydrogen or oxygen, and it's these fixed nitrogen forms that we need for our food chain. So here's a pictorial view of the nitrogen cycle. Farmers from the beginning of agriculture recognized that if they grew crops for more than a few years at a time, they would get lower yields, the soil would lose its fertility, and they discovered very early on that if they spread animal manures, animal waste, or if they planted with peas, bean, clover, plants that we know as legumes, they could restore some of this fertility. And by the end of the 19th century, it was recognized that certain rocks, Chilean saltpeter, could be enormously effective in restoring soil fertility. Well, we know now that the creatures that provide fixed nitrogen for the rest of the food chain are certain bacteria and algae, most of which live in the soil. And these creatures give fixed nitrogen to plants. Plants are then consumed by animals, and the animal wastes and the dying organisms are recycled so that the nitrogen returns to the atmosphere eventually, and this cycle continues. So nitrogen has to be fixed to be used by living organisms, and the organisms at the base of the food chain which do this service are these tiny bacteria. Fixing nitrogen takes a huge amount of energy, and these microbes can do it with solar power. They get photosynthase from the plant, and in exchange they provide the fixed nitrogen. And those of you who are gardeners know that if you pull up a pea or a bean plant, you see these little globes on the roots. And when these globes are doing their job of fixing nitrogen, they're sort of pinkish or purpley. These are called nodules, and they're where the bacteria live and work. Trees growing in sandy soils also have a different species of bacteria in nodules. And they can fix nitrogen from the air. They get very little directly from the soil. Now, in 1918, there was a revolution. Fritz Haber in Germany discovered that he could fix nitrogen in the laboratory. And the significance was immediately clear that we had a way to make chemical fertilizer that would save Europe from starvation. This took a huge amount of energy, however, and knowing what we do now about the need to conserve energy, and knowing what we know now about some distinctly deleterious effects of excess fertilizer, we're starting to wonder if we've got a superpower with fixed nitrogen or a monster. So if you look at the amount of fixed nitrogen that's applied to the surface of the Earth, and this is just a graph from about 1910 to 1990, and you see in that period it doubled. This is the amount that's fixed naturally by bacteria, more or less in balance with living creatures. A small amount is fixed by lightning, and that amount has been doubled with the economic production of synthetic fertilizers, chemical fertilizers. Now, don't get me wrong, this is a great blessing. The world population has grown from less than 2 billion to more than 7 billion now, and this growth has been sustained by an even greater increase in fertilizer use. You can see here the grain yield has doubled between 1960 and 2000, and this is due in large part to increasing uses of nitrogen, fixed nitrogen, smaller degree by the breeding of plants that had better nitrogen uptake efficiency. So this synthetic fertilizer sustains our present population. It's estimated that 3 of our 7 billion people would starve without nitrogen fertilizer. And yet, only half of what we put on the soil reaches the crop. In some areas, only 30%. The rest goes to air and water where we don't want it. It used to be estimated that agriculture was responsible for only a tiny fraction of these greenhouse gas emissions that Professor McCarthy has been telling you about. Recently, we've recognized that nitrous oxide, which comes from fertilizer use and also from the way we're processing our animal wastes, is in fact a very powerful greenhouse gas. I think Michael Diet is going to tell you a little bit more about that. We also use a tremendous amount of energy to produce this fertilizer. Then other problems with nitrogen pollution, when we have irrigation and rainwater pulling the fertilizer through the ground before it's taken up by the roots, it gets into our well water, where it's a problem for human health. The Environmental Protection Agency says anything in excess of 45 parts per million of nitrate in our well water can cause disease, including blue baby syndrome. And when this nitrate runs off the soil into our surface waters, streams, rivers, and oceans, we get algal blooms. As the algae die, oxygen is depleted, and we have terrible fish kills, awful smells, eutrophication, and the huge dead spot that you've read about in the Gulf of Mexico is due to the nitrates and phosphates that have run into the Mississippi River from our farms and then into the Gulf. So here's a pictorial representation of the nitrogen cycle. What we need to do, and we know already a lot how to do this, we need to minimize the runoff into surface waters of nitrate. We need to minimize leaching to well water. And we need to get all the fixed nitrogen that we possibly can into plants and animals where it'll be put to good use. So there are these various places, minimizing, making sure we don't put on any more fertilizer than the plants can actually take up, making sure that we till our land properly, that we minimize leaching, that we treat our animal wastes to minimize the nitrous oxide emissions and the leaching. So the take-home message is that we have a very important human need to balance nitrogen fixation with nitrogen uptake by living organisms. And this is a management problem, and Ann Berwick and Michael Diet will be explaining that difficult as the science may seem, it's really terribly easy compared to the problem of management, because we have to do this not just on a local scale, hard enough, but on regional and now global scales. So this brings me to my last point. We have a terribly important need in our generation to reach out and to teach. And organizations like Concerned Scientists that Professor McCarthy participates in, and our political activities, and in my case, teaching. So I'd like to conclude by just showing you a little snippet of we have a teaching program at UC Davis where we are attempting to harness the emotional power of the arts to enhance learning of environmental science. And I'd like to show you what my students in Earth, Water, Science Song did for their final exam. So if, be patient, I hope that I'm going to have some sound here. So these students heard conventional lectures in environmental science, and then their assignment was to write and perform songs about this. The next assigned topic was fertilizer.
Ann, Berwick?
Oh, could they listen to the song? It's,
Oh, hi, we are called Smells Like Sheep, and our song is called Do You Think? But basically, our song is about fertilizer and how we need a balance of fertilizer. Too much fertilizer, well, fertilizer is basically what I love. Too much fertilizer, you go too needy, you go crazy, and too little fertilizer, you shrivel up and basically die lonely.
they're 19, so everything's about love.
Prevent crazy and prevent lonely, and you just get normal.
Wendy? Okay.
Okay, I'll have to show this to you during the break if you're interested, but it's very good. And when I see the dedication, the devotion, and the energy that these students bring to this particular course, I have hope that we are going to solve these problems.
I'm not going to sing. It's a privilege to speak to you guys. And you've had the privilege of hearing from some really renowned climate scientists this afternoon. And I'm a lawyer and not a scientist, and I work on energy policy. So I'm going to speak from that perspective. But I just want to point out one of the aspects of climate change that the scientists have not focused on today, and that's the concept of runaway warming. Climate change is not just about the elimination of species, about the flooding of coastal cities, about an increase in the range of malaria and dengue fever, and so on, as if that were not enough. The really nightmare scenario is runaway warming. What that means is that an increase in temperatures puts feedback processes in place that will cause climate change to spin out of control. Here's an example. Much of the Arctic is covered by ice, less and less, as you heard. And that ice is white, unlike ice in Cambridge, most of the year. So think about the difference between wearing a white shirt and a black shirt, or between a light road surface and a dark road surface. Arctic ice, like a white shirt or a light pavement, is very reflective and doesn't absorb much solar radiation. When the ice melts, it leaves darker land or water, which absorbs much more heat. And as more ice melts, more dark surface is exposed, absorbing more heat and causing more ice to melt, and so on. Another example is the release of methane, a much more potent greenhouse gas than carbon dioxide, from melting permafrost. Permafrost melts, more methane is released, the climate warms, more permafrost melts, etc. So no one knows exactly where the runaway warming tipping point is. I also want to point out one thing about sea level rise that's so elementary that Professor McCarthy didn't mention it. In the near future, sea level rise will come mainly from thermal expansion. As ocean water warms, it expands. But think about ice again. If you have a drink with ice in it, the level of the liquid does not rise appreciably as the ice melts. But it's a different story if you add ice to the glass. Adding ice does increase the liquid level. That's the difference between ice melting in the Arctic, which is not a landmass, and on Greenland and Antarctica, which are landmasses. When their ice melts and runs into the oceans, the effect is far different, and again, catastrophic as compared to the effect of thermal expansion and of Arctic ice melts. My understanding is that estimates of modest sea level rise in the centimeters are related to thermal expansion and Arctic ice melt, and that the estimates of truly catastrophic sea level rise in the many meters assumes melting of the Greenland and West Antarctic ice sheets. Now I want to turn to energy policy, which is what I really do. Our goal should be and broadly speaking, our goal should be decarbonization of the US economy to the maximum extent possible. Two of the significant paths to follow are, one, decarbonize our electric grid, and two, decarbonize our transportation system through electrification. I'm going to focus here on the electric grid and not on transportation, or for that matter, on land use, which is Michael's topic and also a crucial one. So just to summarize where I'm going, to decarbonize the electric grid, we need to do three things. One, put a price on carbon. Two, prioritize energy efficiency. And three, support renewables and storage technology. After covering that, I'm going to tell you my view of the role of natural gas, of so-called clean coal, and of nuclear power in 10 minutes, Al. So, topic one of decarbonizing the electric grid, a price on carbon. If we lived in a sane world, there would be a federal price on carbon, whether through a tax or a cap-and-trade system. In the absence of sanity, the Obama administration is trying to do the next best thing by imposing carbon regulations on power plants. It's the best the administration can do under the circumstances, but it's a far cry from an economy-wide carbon price. And we'll see how it goes. The Supreme Court has already agreed to review the effort. Okay, so we've hypothesized a sane world in which we would aim for decarbonization of the economy through a price on carbon, which would internalize external costs. So what else would we do? This brings us to topics 2 and 3 on the path to decarbonizing the electric grid: energy efficiency and renewables. Energy efficiency. The cheapest megawatt is the one we don't buy. In the Patrick administration here in Massachusetts, where I work, we call energy efficiency the first fuel. The American Council for an Energy Efficient Economy has ranked Massachusetts the #1 state in the country for energy efficiency, and Boston, as you've heard, the leading city in the country. And I will tell you that notwithstanding that status, we still have huge untapped energy efficiency resources, even without significant changes in lifestyle. Think, for example, about how over-air conditioned your office is, how cold your hotel room is when you check in on a hot day, and about the fuel efficiency of a Prius, about how you leave your water heater on when you go on vacation. Topic 3, renewables. In Massachusetts, we are supporting renewables mainly through renewable portfolio standards, net metering, and a requirement that electric utilities buy a portion of their power through long-term contracts with renewable developers. And I could talk about each one of those for a long time, and I won't do that. Taking solar as an example, with these mechanisms, Massachusetts has gone in 7 years from 4 megawatts of solar energy to over 300 megawatts at present, that's installed capacity, with a solar goal of 1,600 megawatts in 2020, just announced by Governor Patrick, 1,600 megawatts. This is awesome progress of which we are justly proud, although our pride is tempered somewhat when we look at Germany with 34 gigawatts, that is 34,000 megawatts of solar in sunny Germany. But when you're talking really large numbers of megawatts of renewables, with the current state of technology, you're mainly talking wind. Land-based wind in some parts of the country and predominantly offshore wind in New England and the mid-Atlantic. It's my agency that has given the Cape Wind offshore project all its state permits and approved its output contracts, but that's a story in itself. Large hydro in New England, we look to Eastern Canada for that in New England, should also be in that mix. The development of renewables also requires a big infusion of federal research and development money, some of which should go to storage research to enable the use of solar power when the sun isn't shining and wind power when the wind isn't blowing. And by the way, electric vehicles, their batteries, should also be thought of as the vehicles for backing up solar and wind. With respect to research and development, I want to digress and mention 2 things. One, we should stop whining about government subsidies for renewables companies that run into trouble, like Solyndra, and here in Massachusetts, Evergreen Solar. If we were supporting only renewables companies that succeeded, we would be wasting public money on projects that private capital should be supporting. And two, we should acknowledge the obvious, which is that we've been subsidizing fossil fuels for decades in all kinds of ways, for example, through various provisions of the tax code, and mainly by letting fossil fuel plants degrade the environment at very low or no cost. The historic subsidies for fossil plants by virtue of this phenomenon is certainly in the trillions of dollars. So second and third were efficiency and renewables. What's fourth? Is it natural gas in which the country is swimming? I would say mainly only as a transition to renewables. Don't be fooled. Don't be fooled by all the talk of natural gas as a clean fuel. We've been lulled into thinking that natural gas is clean because its combustion has half the carbon dioxide of coal, and it doesn't have some of the other nasty pollutants like mercury that coal has. But the methane that escapes during the extraction, transmission, and distribution processes, and remember from our discussion of permafrost melting what a potent greenhouse gas methane is, has not been accurately quantified. Hey, Wendy, could I have some of my water, please? Sorry. Thanks very much. And then there's hydraulic fracturing and huge historic price volatility. The availability and low cost of natural gas should be thought of as supplying a window of opportunity to focus on the development of renewables. So is fourth clean coal? I don't know enough to say whether this is realistic, but I'm highly skeptical. How much does it cost? What's the parasitic energy load associated with the cleaning? How much energy will we use sending the CO2 off to depleted oil wells or wherever else we intend to transport and store it? And where exactly is it that we intend to store it? Is fourth nuclear? Nuclear energy is bad. Think nuclear waste. Climate change is worse. But I think that debate is largely irrelevant. I would be in favor of building more nuclear plants if that would solve our climate problem, as troublesome as that is, but it wouldn't solve the climate problem even if we had the political will to build nuclear plants, because we can't build them fast enough. Just keeping our existing nuclear fleet in operation and competitive, which we do need to do, is a struggle given the low price of natural gas. So, in summary, where does that leave us if we are to conclude that the answer is other than up a creek without a paddle? Big picture is decarbonize the grid and electrify transportation. Price carbon, prioritize energy efficiency, support renewables and storage technology. Don't be lulled by the talk of so-called clean natural gas. Don't think something called clean coal will solve the problem. With misgivings, keep our existing nuclear fleet operational for the time being, and vote for candidates who are honest about the magnitude of the challenge. Thanks.
Michael Diane.
Thank you. It's very awe-inspiring to follow all the great speakers you've heard. For those of you in Maine, the man we vote for is Elliot Cutler. I'm going to give you a perspective from the trenches, what it's like as a city planner to work with local and regional governments to get 1,200 letters from the Tea Party and try and figure out what's the right direction to go. California, though, has really been in the forefront of climate modeling, amazingly enough, with a lot of the initiatives that Governor Schwarzenegger put in place, and more recently to try and bring land use and transportation together to do the kind of pricing that we heard about, all to meet these targets. And we had the same numbers that Professor McCarthy had for Mayor's Boston plan, 20, 25% mid-century, 80% later. And the challenge for us in the Bay Area, for example, is to say, can we meet those and still accommodate 600,000 new households and 1.1 million new jobs? And we've got a population that's aging. We continue to have people that want to live in suburban communities and office jobs that are going out into the suburbs away from the central cities. And those equity concerns, the fairness questions that always challenge us. And we were asked, I was asked for the fourth time to lead an environmental analysis of what happens when you put money in transportation and trying to achieve compact development. This time around, we were looking at $75 billion in our regional transportation system, of which $65 billion would be discretionary, up to the local control. So the question is, if they're spending that money, does that mean it will just be more business as usual, that line that we saw on the charts that will continue to exacerbate the problem, or can we stay on track with the numbers we've been given in terms of reductions? Well, I'm a kind of good news guy, and the answer from the Bay Area is yes. We can get 7% reductions in 2020 on the per capita greenhouse gas emissions and 15% by 2035. And you add those per capita reductions onto what the state and the federal government are already doing. Our cars, under the corporate average fuel efficiency CAFE standard, are going to have in 2025 an average fleet mileage of about 55 miles per gallon. So the fleet itself is going to become much more efficient. We're looking at a doubling of transit ridership and modest shifts toward more biking and walking. And the emphasis is really on trying to get the transportation systems to be more efficient, to continue to serve people, but not have dramatic, or as the lawyers like to say, draconian shifts in behavior. This can all be done as that chart that we saw with lots of little incremental improvements. We can have just good, more efficient land use, get jobs and housing closer together, and provide those opportunities for people to walk and bike so that they're not always using the car for independent, unlinked trips. And I thought this was somewhat gratifying that the bottom line is we can accommodate growth. We can carry out the targets that we're given from the state and the federal government. And the environmental community doesn't buy into that in all cases, nor do the Tea Parties. But I think it was sort of good that we're being sued on the right side and the left side and by the building industry, because it must mean that we're doing something right as we move forward. Now, I just want to touch a bit on sea level rise. We're looking at a little bit better situation than Professor McCarthy had mentioned, because if you remember that graph, we're on the west coast, or known as the left coast, and we're looking at about 17 to 48 inches at the turn of the century rise. And it's a significant issue from an environmental perspective, but there's a lot being done in terms of adaptation strategies. First, that get us to that lower curve. And in fact, if the bundle of strategies that are available to us are implemented, we conclude, and this is more of a legal term that Ann knows about, that it's a less than significant impact. The challenge, though, is that at the local level, all the elected officials aren't necessarily on board. And I just share then with you in conclusion some observations of this sort of work in the trenches, that we can meet the targets that we're assigned from the state and federal government. Tell us what to do, and we can do it. And we also can provide, I think, more environmental benefits, more green space, more urban agriculture, protection of our resource lands as well. We do have the continued issues that often, whereas we're moving people into higher density housing, accommodating workforce housing, these are in those transportation corridors where you have higher pollutant exposure. So you kind of have the push on one hand to build in your transportation corridors, but the concern that these are also toxic hotspots. So how do you kind of reconcile that issue? And there's a lot of concern about who gets to make these decisions, and that those 1,200 letters I mentioned earlier are all about keeping local control in place. But I think there's a lot to be said with continuing to tear off and give the local governments meaningful targets. Over the long run, though, it will really be the technology improvements that have to make the difference. We can't just do it at the local level. We can do a lot with energy retrofits, with electric vehicle charging, with pricing. In fact, as natural gas pricing and gas pricing goes up, travel goes down, which you'd expect as people want to do less. We've doing a lot with cogeneration and building LED lighting. We're looking at a renewable target of 33% by 2025 for our power generation. And we're trying to, at the local level, say that if you retrofit the buildings, if you get them solar ready, and get your purple pipes in place, then we'll give you a little upside. We'll give you some more density. We can reduce potable water use a lot more water much more efficiently. And in fact, when we're given these kind of CO2 equivalent targets and look at climate action plans, it's amazing that we can usually come up with a reasonable laundry list that doubles or triples the amount of reduction that you needed. So I guess the news from the trenches is that if you give us good numbers, we can work with them and accomplish things. And so I'm actually optimistic about the future and the goodwill that's in place, and with certainly the leadership, as we've heard from the Commonwealth and the university. I hope it will work as well. Al, I think I did it.
Thank you very much.
I brought us in on the time.
Would the other two panelists rejoin us back up here? Another chair? I think we got two chairs here. We'd like to take some questions from the gathered masses here, and maybe I'll start with one. One of the reasons we're here is because my older brother was not a Socrel major like I was. He became he was a scientist, and like the rest of us, gets requests for money, and he was starting to look at the growth in the Alston area, and he's also familiar with tide charts, and he started looking on Google Maps, and he realized some of this land is 6 feet above sea level, others 7 feet, 9 feet. I've got some charts that he prepared that talks about elevation of different parts of the campus, and they're protected by a 12.5-foot bridge, dam. And Sandy would have, with no sea level rise, Sandy would have topped the dam by 4 feet. And so he was saying, well, what is the administration thinking? You know, why are they expanding into a place that looks like it may be vulnerable? And Jim, how much sea rise might we get from a cataclysmic collapse of Greenland or West Antarctica? They're like, is it 20 feet each of them, perhaps?
Well, you don't want to think about the cataclysmic collapse. If all the ice in Greenland melts, and I'm mindful of the feedbacks and the runaway climate concern, which I didn't point out, the really nightmare scenario. If all of Greenland melts, it's 7 meters or 22 feet of sea level. If all of Antarctic ice melts, which is about 10 times that. So it's about 10 times as much ice frozen on Antarctica as there is on Greenland. Antarctica, for a variety of reasons, is not warming at the same rate as the Arctic, and it's kind of complicated. It has to do with ozone, but also has to do with the fact that it's high. Antarctica, like Greenland, rises steeply. Antarctica is it's the coldest continent. It's also the highest average elevation of any continent. So when you add elevation, the effects of temperature, of course, they're vertically scaled. But if you don't have to lose all of Greenland to have a serious problem, and even though, you know, it's great knowing that the coast of California can maybe accommodate this, we didn't say anything about the rest of the world. And if you look at what a meter of sea level rise does to Bangladesh, it's horrific in terms of the displacement of people. If you look at what a meter of sea level rise does to many major cities that are not as prepared as we'd like to think much of North America is to deal with this. So locally, though, I mean, the point you raise is one that I would say has received precious little attention on this campus. Maybe someone here knows, maybe Harry knows. I know that I have colleagues who have raised this question, and particularly given that most of what planners have been dealing with up until very recently have not, in terms of sea level rise, have not taken in consideration ice melt from Greenland.
I was struck when I was thinking about preparing for this about the issue of methane and some of the other equivalents and how they have a much shorter life in the atmosphere. So that thinking about the opposite of the cataclysmic event, that maybe we can be doing things on these other sources to have very early interventions that might address, because of the multiplier effect, the trend and get some reductions in a faster time frame than some of these longer term efforts.
Yeah, I mean, it's true, methane has about 25 times the warming potential of carbon dioxide, but carbon dioxide, unfortunately, persists in the atmosphere for 100 years. Methane has a shorter lifespan, but there's just a lot more carbon dioxide being emitted. And so, you know, the bottom line is we have to work on all of these possibilities, but we have a really significant problem by virtue of the fact of the magnitude of carbon dioxide emissions and the half-life of carbon dioxide. And so I wish I shared some of the optimism that you've heard here, but I think, you know, obviously because of the half-life of carbon dioxide, we're going to have to get a handle on this problem very quickly. We're talking a decade, I think. Again, I'm not a scientist. And I have no doubt that it is possible with the political will to get a handle on what needs to be done in a decade or 2 decades. But you know, we have the technology, I think, already, but we don't have the political will at the moment. We do in some parts of the country. I think we do in Massachusetts. Maybe I don't know that much about California. I understand we may well, but you know, that's not exactly where we need political will at the moment.
Jim?
Well, just very briefly, I do agree that the methane, which has a lifetime in the atmosphere of a dozen or so years, in some regards is a more tractable problem. Another one that has enormous significance for the Arctic is soot. The black carbon from combustion of diesel and also biomass burning. And it is one of the reasons that we now think the Arctic is warming as fast as it is. It's not only the positive albedo feedback that we heard described, but also the fact that atmospheric transport carries these fine particles of soot onto ice and snow. And we all know about increasing forest fires and wildfires in Australia now, but also the West, but also in the boreal north. And there's an area where it's clearly the result of just warmer, drier conditions and occasional lightning strikes. So if forest fires in Alaska, for example, upwind from Greenland. But just a word about optimism. Yeah, the reason I'm optimistic, two things. One, the progress we've seen in the last decade and the fact that it's irrefutable, that it's not that difficult to do what needs to be done. All the projections, Michael and I were talking earlier in the late 80s, early 90s about what it would cost to get sulfur out of stacked gas and the elaborate process that first President Bush approved, a cap and trade system to reduce sulfur, which was creating, acid rain and all the problems in ecosystems and buildings and human health and everything else. And it was done in a way that was far simpler, it cost less, it happened easier than all the projections. Technology kicked in, the cost of getting sulfur out of stacked gas plummeted. So, we're seeing some of that now. I mean, who would have thought just a handful of years ago that we'd have the success that we've had with wind and solar installations and the price coming down? People like Harry and Jim Engel with solar in their homes. Who would have thought that available to us even a decade ago in this area? But I'd have to say, the one thing that also makes me very optimistic about this is what I do most days on this campus, and that's interact with college-age students, and the number of them who have this in their head, no matter what they're going to do, whether they're going to be an attorney or a business person or a scientist, they're going to make a difference in this area. The number of students who are really committed to seeing this as the issue of their generation. And that gives me inspiration every day.
Are there some questions from the line up at the, yes.
Is it on? Oh, good. I'm Gary Bean. I'd like to share with you some research and get your reaction from it. This is centered around Professor Johannes Lehmann over at Cornell's Soil Science Department. And the research goes back about 30 years to its beginning. There are areas along the Amazon and Rio Negro where apparently the pre-Columbian farmers turned their corn stalks into charcoal rather than composting them. They are the only areas in the tropics where you can have sustainable agriculture without doing slash and burn every 3 years. The research to try to figure out what's different about these soils is that the charcoal acts as a sponge to absorb nitrogen and other nutrients and water, and makes them available to the plants rather than having them run off in the tropical rains. They dated the charcoal, and the youngest was to be expected about 500 years old before the European epidemics caused a population crash. But the oldest was several thousand, and this was in tropic environments. They've since done research and found that you can add up to about 150 tons of charcoal to soil and reduce the need both for fertilizer and water and increase the microbial activity. It also reduces the runoff of nitrogen fertilizer and the need for adding compost. So you can take by about 75%. The way of making charcoal is to take the volatiles that come off the plant material, burn them, and use them to heat the plant material, and only a small percentage of the charcoal ends up being released. There has been work, and I've been working on research to take that extra energy and make electricity out of it. It seems to be a credible way of sequestering carbon, Under the Clinton administration, they began an initiative called Seaside, carbon sequestration. I think they called it in terrestrial ecosystems. It languished under the Bush years. I'm wondering, is there any research that has discredited this? And if not, does this sound reasonable to you?
Wendy?
I assume that you're talking about what we call biochar. Yeah, there's a lot of research being gone on right now, and people in ag research are actively trying to see whether we could incorporate it into our horticultural practices here.
Let's take one over here.
Thank you. I'm Chuck Lavelle. I'm a medical doctor. I, like many of you, are probably concerned about the lack of transparency in genetic modification of plants. Of course, my perspective is from the health perspective. Since plants play such a vital role in both the carbon dioxide cycle and the nitrogen fixation cycle, should we also have concern about a loss of efficiency in either of these cycles as we rush into genetic plant modification?
Oh, that's a very broad question. There are people on both sides of the fence, people that say that to save our soils, we're going to need genetically modified plants. I'm having a senior moment now. There's a good book written by Pam Ronald called Tomorrow's Table. She is a molecular biologist married to the head of the organic farm, student farm at Davis, and she talks about their dinner table conversations. There are ways in which organic food production is very sustainable. There are ways in which genetically modified plants may in fact help us to conserve our planet. So my feeling is that we need to understand how each of these organisms is going to function in the environment. We have to be pretty careful about that. I also think people do have a right to know what modifications have been made. But I think there is potential in the use of genetically modified crops, helpful potential.
Up here, please.
I am Ken Chang. I have a question for Anne. You have a great program here, the Green Communities in Massachusetts. Mm-hmm. And I see that one of its first criteria is that these communities must provide sites for renewable energy generation. And my question is that succeeding? Are there community solar being generated here from that program? And the second half of my question is for Michael, and that is, in California, is there any chance whether we can get community solar and community-based renewable energy going?
Yeah, so thanks for your question. So my agency, which is the Department of Public Utilities, doesn't actually run the solar programs, but I do know obviously a bit about them. I think the most interesting sort of community-based solar program coming out of the Green Communities program under the Green Communities Act has to do with what's called Solarized Massachusetts. So what happens is depending on if you get enough people in say Cambridge to sign up to put solar on their homes, then everybody gets a reduction in the price. And also just the mechanics of getting it on your home is kind of facilitated by the program. So I actually just recently put solar on our home in New Hampshire, and it took me, with a fair degree of sophistication about these issues, many hours, together with my son who works for a solar company, to figure out exactly the details. So Solarized Massachusetts helps you just sort of speed through that stuff and also lowers the price depending on how many people participate.
The reason solar on the roof is much more difficult than community solar is just as you described it. There are many folks out there who would love to be
Yeah.
part of this effort,
Yeah,
but just the problem of actually getting it on your roof
yeah,
and then be responsible for maintaining it
yeah.
is,
Well-
is an issue, whereas community solar, which is a beautiful program where you buy into a massive net metering establishment. And, you know, for Michael, the question is, if in California we allowed community solar, then Lennar, KB Homes, et cetera, when they build their 1,000-unit projects, they could provide this.
Yeah. We have in Massachusetts, a program which I won't start to explain because it'll take me too long, but called virtual net metering, which accomplishes, I think, pretty much the same thing as what you're talking about with community solar. But, you know, the bottom line is there are all kinds of mechanisms for getting solar out there in a much sort of more expedited way than we started with. We also have in Massachusetts, and I'm sure in other states too, what are called PPAs, purchase power agreements, where a company puts solar on your roof, they own it, you lease it, and you enter into a contract where your price for power is kept below what you would get if you were getting power off the grid. And so you don't have the upkeep, the maintenance responsibilities, and you don't have the capital costs. So,
A quick follow-up. We have some interesting programs in California called community choice aggregation, where communities can create their own energy authorities and then Consolidated Edison or Pacific Gas and Electric still deliver to the homes. In Marin County, they created one that would then be committed to a much higher renewable percentage, and people can even sign up for a Tier 1 or Tier 2 to get 100% green. The municipal authorities, like the city of Santa Clara, which has high Google use and all of the, is producing tremendous amounts of power. So it's a combination of the programs that you heard at the community level, but also, which I think is very exciting, this community choice aggregation, and then PG&E is really afraid of that, so they'll come in and be much more responsive because they don't want to be losing the power generation.
Okay. And I would ask my classmates to think, would it be appropriate for Harvard, when asking for a donation for construction in Alston, should they disclose the risks involved, the chances, the expected sea rise, and the possibly catastrophic? I've learned recently the difference between climate scientists' projections, which are on the low side, it's something that can be established by science, versus the pragmatic consideration of an engineer who's supposedly looking for events that maybe there's a low probability that could happen and high consequence. Well, nuclear power plants. I mean, what if you had a bunch of people get together in terms of regulating a nuclear power plant, and they say, well, how many of us think this is going to be okay to the rest of the century? And well, a few things could go wrong, but we don't, we can't model the problems. I mean, what if, why should the approach with nuclear safety, should some of the engineering and some of the safety levels, should that wash over into the way we deal with climate change?
You'd want to do it better.
You'd want to do it. I want to do it better.
See if we can get them.
yeah.
Okay.
My question is about the first PowerPoint show to Professor McCarthy. Could you possibly post that? I found all of the data astounding, overwhelming, completely unknown. And how could I go back and review what you demonstrated to us so quickly and really study it and go in deeper. I caught a few of the websites that were your sources, but not many.
Yeah, I think there's a citation on everything, but I'm happy to make it available in any way you want.
Okay, I'll see you
Could-
afterward.
Yeah, could,
If we get the deck, we'll put it on the Class of '68 website.
okay.
That's a
You'll
great
be there,
idea.
since I, we're all at home here, but when I lecture other places, I always say, if you want to follow up on any of this and want access to any of those materials or discuss them further, just let me know.
Okay, we're trying to get through how many people we can.
Ann mentioned the Supreme Court taking cert in the case involving the EPA's authority to regulate stationary sources of greenhouse gases. I'm not sure if you can speculate what they'll do, but if they were to rule against EPA, do you think that that would be catastrophic in terms of controlling greenhouse gases? And if so, do you think there's any political will to amend the Clean Air Act?
Well, that question has a lot of important ramifications. I mean, the Clean Air Act, well, first of all, it's a case, I'll brag a little bit, the case of EPA, Massachusetts versus EPA, is the one that established the ability of the Environmental Protection Agency to regulate carbon dioxide under the Clean Air Act. And that case was actually litigated by a lawyer who's now a judge in Massachusetts, who was my deputy when I ran the environmental division of the Massachusetts Attorney General's office. So I'm very proud of the work that he did and that the Attorney General's office did in that case. That said, the Clean Air Act is not the best way to regulate carbon emissions for a whole bunch of reasons, which we could talk about if we had more time. The best way, as I said, is to put a price on carbon economy-wide. So because it's not a great way to regulate carbon emissions, it's something, it's a gazillion times better than nothing, but the scientists don't use the term gazillion, but because it's not the best way to regulate carbon, it is not as far-reaching as an economy-wide price on carbon would be, and I don't think it would be catastrophic if the Supreme Court struck it down. I have no idea what the Supreme Court will do. Also, the case that's before the Supreme Court, it's my understanding, just has to go with the EPA regs that are final, which are the regs that address new coal-fired power plants, of which virtually none are being built in this country. So that regulation doesn't have really a very broad effect because it's just addressing new power plants. The administration has supposedly on its drawing board regulations for existing coal-fired power plants, regulation of carbon from existing coal-fired power plants. If those ever get actually into, if those become finalized, they would have greater reach, but I think really a lot of the work that needs to be done in terms of coal-fired power plants is being done in two ways. One, existing regulations on mercury, and which is going to have a big effect, going to make a lot of coal-fired power plants uneconomic. And the other, moderate, I don't want to say death knell, but bad news for coal-fired power plants is the low price of natural gas. So that a lot of coal-fired power plants are simply becoming uncompetitive for that reason. So, I'm glad the Obama administration is doing what it's doing, but I don't think it's the holy grail.
Okay, over here.
Okay, two comments and a question. First on solar, Concord, Massachusetts, where I live, is not part of the Normal grid. We have our own power plant. And so we didn't participate in the Massachusetts Solarize program, but somebody decided in the town to take it on themselves to do their own equivalent program. We've now apparently signed up about 120 homes over the 100 goal, and it looks very good. I got the pitch and signed up being a cheap Yankee. I looked at the numbers, and it was a four-year payback, so it's fairly...
How many years?
4-year payback. 4-year payback,
Mm-hmm.
4 kilowatts of power. So we'll see. Okay, the main point I was going to make, though, was about a technology that has advanced faster than I had it suspected it would, and it's the light-emitting diode, regular lights for houses. The attempt to replace tungsten lamps by compact fluorescence was fairly ugly with some of the results we've ever tried to use those lights, especially outside in cold weather. If you manage to wait 5 or 10 minutes, you might eventually see some light coming out. But what's come along and surprising in terms of technology was the ability to mass produce fairly high-power devices equivalent to 90-watt lights. They basically take about 1/5 the power of a regular incandescent light with the same lighting efficiency, given that lights take about 20% of the power generation capacity in the US, I think. That's a significant impact. I've just relamped my entire house, and the reason I'm able to do it is that when you go to Costco, you get an enormously good break from NSTAR, who's subsidizing the lights. I would suggest to all of you, if you live in Massachusetts, to look into doing it because it's a good deal. I'm saying this by sticking my neck out. These Chinese-made lights claim they will last 22.8 years. I don't know who got that precisely. And hopefully they have made them correctly. All right, if they do, they are a great deal. My comment to the state of Massachusetts is these are only available with this great subsidy in limited quantities through Costco. Is there any way that this can be made more available throughout the state so it can be more widely adopted?
No, these lights are being subsidized. It's not just through Costco. The subsidy is much broader than that. Also, what town do you live in?
Concord.
Yeah, so you have, so actually you're, I don't mind, you're a free rider.
Yes.
In the sense that, so he lives in what's called a muni. That is, he doesn't get his power from a big investor-owned utility. He gets his power, as he said, from a municipal light plant, which
Who buys it from, of course, the grid.
But we don't regulate it.
Yes.
And so the rest of us pay a system benefit charge that funds the subsidies for those light bulbs, and you don't pay that.
I know that, thank you.
Okay, I just want to be clear.
But
I'm fine with it.
My question is, where else can you get these great prices? Because it's less than $10 for a 60-watt equivalent bulb, which is unavoidably good.
Yeah, it's not just Costco.
All right.
We just got a few more minutes. Try to just go to your question.
Oh, okay. I have a comment, though. A comment first. Briefly, I have spent a lot of time in New Orleans, and I live in New York. Since about 1965, New Orleans went through meeting after meeting after meeting, trying to decide what they were going to do about sea level rise and the diminishing marshes that might protect the city. It took 30 years before anything really concrete was developed. Finally, right after Katrina, they got their act together and put up levees that could protect the city. Hurricane Isaac came through last year. The city barely escaped flooding. New York, where I live, experienced Sandy a year ago. And now New York, I see, is in the same situation as New Orleans. They can't make up their mind what they're going to do, whether they're going to put up hard structures or whether they're going to construct a lot of soft structures, i.e. marsh building, sand dunes, and these kind of more fragile reconstruction efforts. My question goes to Michael. Is there anything going on in San Francisco which has many low-lying areas to protect the city, even though you're on the left side and you don't have too much sea level rise to worry about? Something is coming. Are there any measures that you know in San Francisco?
Yes, there are, both at the regional and the local level, adaptation strategies. And there also is a lot of good work done on what's called extreme landscape design, coming out of Holland and Europe in terms of welcoming in the water.
Yeah, Sacramento is much more flood prone than anywhere else in the country at the moment. We're in greater danger than New Orleans was before Katrina. And there's been huge amounts spent on improving levees, Also a sense that people that build in the floodplain really need to buy flood insurance, and that's being mandated. And overall, just a recognition that floods are a fact of nature. It's not if, it's just when. And you have to recognize the power of the river.
What are the prospects for carbon dioxide sequestration?
Question, what are the prospects? So the notion being that if we could, as Ann was saying, capture CO2 from any fossil fuel combustion facility, coal, gas, biomass, and then in some way secure that in a reservoir that would hold it indefinitely. So the initial notion, and this is the technology exists because the oil companies do this now. They pump CO2 into the ground to force oil out, tight oil out of rock that is otherwise not releasing the oil, often involving fracking to do that. But the big question is not whether it can be done; it's whether it can be done at a scale that would really make a difference. And it's it's the back of envelope kind of calculation that you can see at a tip one way or the other. Clearly, in the ideal circumstances, you would build a plant proximal to an ideal reservoir. But and so we're not likely to build more coal-fired power plants. You remember Vice President Cheney's plan was to build 200 new coal-fired power plants, mostly by now, and the score on that is virtually nil for that initiative. So gas plants, this would be where you'd want to do it. And I honestly don't know if anyone has made a serious effort with this surge and transformation to gas to see what the practicality of that is. And we come back to, where's the incentive, where's the initiative? We had a big burst of research early in the Obama administration to explore prospects of this. There have been some private sector. But to the best of my knowledge, there's still nothing that looks terribly encouraging on that. Ann may have it.
I'm sorry to be the wet blanket around here, but remember what we said about nuclear power, which is, even assuming you think nuclear power is a good idea to address climate change, not going to do it fast enough. And to my knowledge, and again, I'm not a scientist, but there's nothing going on, or close to nothing going on, in terms of carbon capture in natural gas plants. And so let's say we start doing that today, which we're not, and then, so we've got to develop technology to capture it. Those plants are going to be much less competitive than existing natural gas plants because there's a significant parasitic load, energy load associated with the capture technology. Then you got to transport the CO2 presumably to the saline aquifers, because those are the biggest potential potential storage reservoirs. And then, it's sort of a wing and a prayer in terms of whether you think on that scale they're going to actually retain the CO2 for millennia. So, you can put money on that one if you want, but.
Hi, I'd just like to offer a couple of resources. I do a local radio program on climate change, and part of that program is downloading a program called EcoShock Radio. It's ecoshock.org. You can all listen to it. It's quite a wonderful program. Another resource, This Deep Future, he talks about carbon dioxide over a 100,000-year period, given a couple of different scenarios. Bill McKibben has written about the numbers: 2 degrees, 565 gigatons, and 28K resources in the ground. In that context, I loved what all of you said. It was wonderful, and I'm glad to be in the same class as all of you. I loved especially the part about the art, because I think part of what really is powerful is that I think we live in the hospice for the Holocene. This period of time that we're living is ending very quickly. We're in the Holocide. There is an Ozymandian epilogue that is currently happening. We will be dead, all of us and our offspring, in 100 years. Unless enlightenment happens. Really, the only antidote would be for people like yourselves to be in charge. There are... No, it's true. It's true. It's true. The people we have in charge are thinking about the Keystone XL pipeline and express keystroke surveillance of scientists who are not with the party line. Part of what feels so powerful, I think, humanly, is to feel we have a stage 5 cancer diagnosis, and we have to come to terms with our own ending.
Okay, it's 4:04, so I'm gonna thank our Jim and our distinguished classmates, and I'm very glad finally to have figured out what the solution is. Just have the class of '68 run everything, and then everything will be all right. Thank you.
Thanks.
Thank you. And again,
Thanks.
I have